Okay, everyone, before I begin completing some of the problems with you guys, I want to introduce some of the equations that you guys may not be familiar with from class. So in class, we've already seen the equation for gravitational potential energy. We saw the equation for kinetic energy, but what about the equation for elastic potential energy, which is equivalent to 1/2 times K times X squared. So it's understood here that K in this equation stands for what is known as our spring constant, and X here stands for the distance stretched or compressed. Okay, this term K here, all this term means, the spring constant, is nothing more but a representation of the magnitude of stiffness. So different springs and different rubber bands, depending on the material, they have different values to describe their stiffness. In other words, their resistance to being stretched. So the higher the K value, the stiffer the spring or the rubber band, meaning that they have a greater resistance to being stretched. Okay, X here just represents the distance you stretch your spring or the distance you compress your spring. And of course, you also have this equation right here. You're going to need this equation for this assignment that says that the force of your spring is equal to K times X, the spring constant times X. Okay, so with that said, let us do number 2 together and number 4 together, because we have not worked on these problems, and we have not worked on these types of problems in class. So I just wanted to do these examples with you guys. The rest you should be able to do on your own. Okay, so let's look at number 2 first. Number 2 says a linear spring has a constant of 377.16 newtons per meter. How much force is necessary to stretch it 0.39 meters? Okay, so if we go back here, since we're finding for force, that means we're going to use this equation right here, and the force of a spring is equal to Kx. So again, we're working out number 2. Okay, and we're solving for force. So number 2, the force of a spring is equal to Kx. So we're solving for force, but we're given the spring constant K, which is 377.16, and we're given the distance stretched, which is 0.39 meters. Okay, so all you have to do is multiply those two together to find the force, which is 147.09 newtons. Once you put that in your calculator. Sorry about that. I accidentally hit that button. Okay, and so 147.09 newtons is the force required to stretch this spring this distance. Be sure that you include your units. Since you're solving for force, your units should be in newtons. Okay, let's look at the last one that we're going to do together. Let's look at the fourth one. Okay, the fourth one says Benson's mountain bike has a spring with a constant of 64 newtons per meter in the front wheel suspension, and it is compressed 0.17 meter when she hits a bump. How much energy does the front spring now store? Okay, so energy, if we're solving for energy, that means we're going to come over here and use our elastic potential energy equation. Okay, so let's do that now. Again, we're working out the fourth one. Okay, so elastic potential energy, which is what we're solving for, is equal to 1/2 times the spring constant K times X squared. So let's just plug everything in. So 1/2 times 64, where it's understood that 64 is the spring constant K, times 0.17 squared. Okay. And all of this tells us our elastic potential energy. Okay, so if you put it in your calculator, if you multiply all those terms, this times this times this, you should get a final result for your elastic potential energy. Your final result should be 0.92 joules. Again, as you're solving for energy, be sure to put your units in joules. Okay, so that's how much energy the spring on this bicycle possesses the moment that you hit a bump while riding the bicycle. Okay, and that's number 2. And number 4, if you have any questions, please come see me.